Let's say that a ray of light travels from air into another medium, making an angle serious 1 equals to 45 degrees with normal. So find the angle of refraction if the second medium is fused quartz, carbon disulfide, and water. So they use three different second mediums, and then we must find then the angle of refractions for that second medium. So basically, let us start with the first case, that is fused quartz, right? And then we say, well, if we use the Snell's law, I know that based on the Snell's law, we have that N1 sine of zeta sub 1 is equals to N sub 2 sine of zeta sub 2. Okay? Now, we know that for the air, M sub 1 is 1.000293. Here, this is the medium 1. Right? And it's air. And therefore, for the fused quartz, we have the medium 2. We have that based on tables, that I showed you previously during the lecture, the index of refraction would be 1.458. This is for the fused quartz. So the mean now we're ready, to apply this new law, because we know also zeta sub 1, that is the angle of incidence, which is 45 degrees. And then now we're ready to find the Snell's law. So in the Snell's law, the unknown in this case is just zeta sub 2. So we're going to solve for that unknown. So we say that N1 sine of zeta sub 1. So we say that N1 sine of zeta sub 1 over N sub 2 will be equals to the sine of zeta sub 2. Now we're going to apply the sine inverse. So we can say that the sine inverse of N1 sine of zeta sub 1 over M2 is going to be equal to zeta sub 2. We can now substitute, and we can say that zeta sub 2 is equals to the sine inverse of what is M1, the index of refraction of the medium 1, that is 1.000293 times the sine of 45 degrees, that is the angle 1, divided by the index of refraction of the second medium, that is 1.458. So when we do these calculations, we will get that in this case, zeta sub 2 would be equals to 29.02 degrees, or approximately equals to 29.0 degrees. So this is the angle of refraction when the second medium is fused quartz. Let's do the same calculation now for carbon disulfide. So now in the case of carbon disulfide, we have that M sub 2, so the index of refraction would be based on the table 1.628. This is the index of refraction of the carbon disulfide. And then if I apply the same equation that I found here to find zeta sub 2, I can say that zeta sub 2 is the sine inverse of n1 sine of zeta 1 over m2. Now, what is n1? So sine inverse of m sub 1 is the index of refraction of the air. So it's going to be 1.000293. We have the same angle of incidence, that is 45 degrees, so sine of 45 degrees. And what have changed now is the index of refraction of the second medium, that is the carbon is on 5. So we get divided by 1.628. And we're going to have that zeta sub 2, so the angle of refraction for the second medium will be 25.75 degrees, which is approximately 25.8 degrees. Okay, I am writing my results with 3 significant figures. We have one last calculation to do. That is when the second medium is water, right? So when the second medium is water. So basically the same thing. Second medium is water, so the index of refraction of the water would be 1.333, which is for water. I'll apply the equation, that I found here when I solved for zeta sub 2 in my first case. So we say that zeta sub 2 is the sine inverse of n1 sine of zeta sub 1 over m sub 2. So it would be, sorry, the sine inverse of 1.000293 times the sine of 45 degrees, all divided by 1.333, that is the index of refraction. So we will get that zeta sub 2 in this case will be approximately equals to 32.053, which is approximately 32.1. So there I found, as you can see, the angle of refraction for my 3 second mediums. In the first case, a second medium that was fused quartz. Later we have another medium that was carbon 5. And finally we had a third medium that was the water. So we found in this case this angle of refraction. Now, I would like just to analyze something with you. The refractive index of the fused quartz was lower than the refractive index of the carbon 5, right? But we found, that the angle of refraction of the fused quartz is higher than the angle of refraction of the carbon disulfide. So in the case of the fused quartz, right, the refractive rate will move a less angle or a lower angle away sorry, in this case, toward, by the way, just toward the normal, right? But remember that we said that as higher the index of refraction, the more that the refractive rate will bend toward the normal. So for this uh, higher index of refraction, then this angle is lower, what means that, for this higher index of refraction, the refractive rate move more, toward the normal. So we have moved more toward the normal. It's closer to the normal. Okay, so that is an important conclusion from this part, and that corroborates, what we mentioned in the theory. Any questions so far? Well, let's see a second exercise now. In this second exercise, they say an underwater scuba diver sees the sun at an apparent angle of 45 degrees from the vertical. What is the actual direction of the sun? What is the actual direction of the sun? So we have an underwater scuba diver, and he sees the sun at an apparent angle of 45 degrees. But we want to know what is the actual direction of the sun. So how we solve a problem like this one? Well, I will represent here, the boundary between the air and the water. Our scuba diver is under the water. This line represents the normal line. And then our scuba diver, when he look at from the bottom, from under the water, when he look to the sun, he sees the sun at an angle of 45 degrees. So basically, this is what happens. This angle is 45 degrees. This angle is also 45. But that is not what really happens. So this is just basically, an apparent scenario. So what happened in reality? What happens in reality is that we have the water surface here. We have the normal. So the incident ray, when it's refracted, as below we have water with a higher index of refraction, needs to move toward the normal, right? So if the scuba diver sees the sun at 45 degrees here, it's because really the sun is at a higher angle. So we can say, okay, this is my incident ray. This is what the scuba diver sees, right? This is my incident ray. And this is, now my refractive rate. And this is the sun at 45 degrees. what really happens here is that this is my incident rate. Of course, we know that this is the normal. And now the angle theta 1 is higher than 45 degrees. Now remember the eye of the scuba diver is here. We erase the second. Is to represent the eye of the scuba diver. So he's just looking at the sun. Sides, right? And of course, we have water as is needed. This is water. So the angle theta 1 is not really an angle of 45 degrees. Because as we are going from air to water, what happened with that rate is that it have moved toward the normal. So the incident rate needs to be at an angle of more than 45 degrees. So we're going to now calculate that. So we know that in this case, m1 sine of theta 1 using the sense law is equals to m2 sine of theta 2. We want to calculate, in this case, theta 1. So we're going to say that this theta 1 that we found before will be the sine inverse of n2 sine of theta 2 over n1, where n2 is 1.33 because it's the index of refraction of water. While m1 is 1.0009293 because it's the index of refraction of the air. Because it's the index of refraction of the air. So we can now calculate theta 1, so the real, the real incident angle, so will be the sine inverse of what is m2, 1.333 times the sine of 45 degrees, because this angle is 45 degrees, the refractive angle, divided by m1, that is the index of refraction of the air. And when we calculate theta 1, we will find that theta 1 will be 70.44 degrees, with respect to the normal. Usually, when we try to find, for example, the angle of when the sun is at some time delay, what we calculate is what is called the angle of elevation. And the angle of elevation is the angle with respect to the surface of the air, right? So if that is theta 1, there will be one angle here that is going to be this angle that we call angle of elevation. And if you want, I can call that angle of elevation. Let us use another uh, letters that we call angle of elevation beta. So I know that this angle of elevation beta would be 90 degree minus zero 1. So my angle of elevation beta would be 90 degree minus zero 1. We said that is 70.44 degrees. So beta, my angle of elevation would be 19.56. So basically, if we calculate this angle of elevation, what we say is, okay, when you measure the angle of the sun with respect to the surface of the air, that angle, that is what we call angle of elevation, is equal to 19.56 degrees. So this one is with respect to the air surface. And in this problem, we found then what is the actual direction of the sun. The apparent direction was 45 degrees from the normal, from the vertical, from the perpendicular to the surfaces of the air and water, on the boundary, between the air and the water. But the actual angle with respect to the normal was 70.44 degrees, and the actual angle with respect to the air surface was 19.56. So this is another example of how we can calculate using distance law, uh, the angles. In this case, the actual angle or the actual direction of the sun. I have another problem here. Let me just use some markers so I know what I use to explain these problems. Just like that, for the review, we have some more problems. The second one also, I explained it. This other problem was also explained. I would like to explain now this one example. Let's say that it says that a laser beam is incident at an angle of 30 degrees to the vertical onto a solution of calm cider in water. If the beam is refracted to 19.54 degrees to the vertical, first, what is the index of refraction of the cider solution? Suppose the light is red with a wavelength of 632.8 nanometers in a vacuum. So find its wavelength, find its frequency, and find also its speed in the solution. Find its frequency and find its speed in the solution. So basically, the first we need to calculate the index of uh, refraction, the index of refraction. So we have here the 2 medians, right? So we have one medium here that is the air, and we have the other medium that is the carbon side. Now, we have here the normal, and then I have an incident angle that comes from the air, or an incident ray. And this incident ray is an angle of 30 degrees. And then we measure the refracted rate, the angle of the refracted rate. And when we measure the angle of the refracted rate, you know, this refracted rate is this rate. And it is an angle of respect to the normal of 19.24 degrees. Of 19.24. So what we want to know, we know the index of refraction of the air. We know that this index of refraction is 1.000293. But we don't know the index of refraction of the corpuscle. This is the number. So this is what we want to calculate first. So again, we use the Snell's law. So I would say, well, if I have to calculate n sub 2, I will say that n sub 1 sine of zeta sub 1 is equal to n sub 2 sine of zeta sub 2. Right? We want to find n sub 2, so we will say that solving for n sub 2 index of refraction of the medium 1 times the sine of zeta sub 1, which is the angle of incidence, divided by the sine of zeta sub 2. Remember that zeta sub 2 is the angle of refraction. All this will be equal to n sub 2. We substitute now. And we get that n sub 2 will be equals to m sub 1, so index of refraction of the medium 1, which is 1.000293. Sine of zeta sub 1, which is 30 degrees, divided by the sine, of zeta sub 2, there is 19.24 degrees. So when we calculate n sub 2 with that data, we're going to get that n sub 2 is 1.517, which is approximately 1.52. So 1.52 will be the index of refraction of the desired solution. Now, they give us some more information that is going to be important to calculate, you know, the other part of the problem. So they say that the light, you know, is red light, and that red light have a wavelength in vacuum of 632 sorry, 0.8 nanometers. So what they want that we find the wavelength in this Siren solution. They want that we find the wavelength in this Siren solution. So remember that we said, that when a light ray goes from one medium to another, the wavelength is going to change. The wavelength is going to change. So the wavelength of this red light of 632 nanometers will be different once the light is in the Siren solution. Now, one of the expressions that we discussed in the lecture is one formula that says that the relation between wavelength and index of refraction for the two mediums is this: the wavelength of the medium 1 over the wavelength of the medium 2 is equals to the index of refraction of the medium 2 over the index of refraction of the medium 1. So wavelength in medium 1 over wavelength in medium 2 is equal to index of refraction of medium 2 times index of refraction of the medium 1. We can rewrite this if we make cross multiply, like wavelength of 1 times index of refraction of 1 is equals to the wavelength of 2 times the index of refraction of 2. Solving for wavelength of 2, we get that the wavelength of 2 would be the wavelength of 1 times the index of refraction of 1 divided by the index of refraction of 2. So this wavelength of 2 would be the wavelength of the red light in the Siren, the current Siren solution. Why? We know that wavelength 1 is the wavelength of the red light in the air, or in vacuum in this case, but always vacuum and air are very close bodies. So that means that now I can just calculate this sigma, this lambda 2, which is going to be 632 nanometers. That is the wavelength in medium 1 times the index of refraction of the medium 1, that we know that is the vacuum is 1.000 divided by the index of refraction of Siren, which is 1.52. So you will find that the wavelength, of the red light when propagates to the core Siren, it will be 416.3 nanometers. So here we have the value of the wavelength, in the core Siren. So we got a lower wavelength. We got a lower wavelength because we had an increase in the index of refraction. Now, also they ask you to find the frequency And we know this. We know that at vacuum, the speed of the light, or the speed of the light beam, in this case, this red light, is equal to the speed of light. It's 3.0 times 10 to the 8 meters per second. So if I want to now find the frequency, and I know that the speed is equals to the wavelength times the frequency, if I solve for frequency, frequency is equals to the speed of the wavelength, right? So I know the speed of light in vacuum, and I know the wavelength of the red light in vacuum. So I can say that in this case, the speed of light is 3.0 times 10 to the 8 meters per second divided by the wavelength in vacuum, which is this given value of 632.8 nanometers. Remember that nano is 10 to the negative 9, so 632.8 nanometers will be the same if we convert this into meters, 2 times 10 to the negative 9 meters. So when we do the calculation, we will get that the frequency. Remember that the units of frequency are hertz, and hertz is second to the negative 1 or 1 over second. It would be 4.74 times 10 to the 14 times 10 to the 14 hertz. So that would be the frequency of this red light, you know, when it's in the uh, in this case when it's in vacuum. Because we're using, the wavelength in vacuum, so that frequency is in vacuum. But remember that the frequency, we said in the lecture that the frequency doesn't change. The wavelength change, the speed of the light change from one medium to another, the wavelength change from one medium to another, but the frequency doesn't change. So the frequency of this red light in vacuum will be the same frequency that this red light in the condenser. The last question is the speed of the light in the condenser, so in the solution. And well, the good thing is that this speed, we know that is the wavelength times the frequency. We know the wavelength. We know the wavelength in the condenser, that is 416.3 nanometers. And we know the frequency, so we can just use, this relation. So the speed in the condenser will be the wavelength in that condenser, that we said that is 416.3 times 10 to the negative 9 meters, and the frequency, and we said that the frequency doesn't change in the medium, that is 4.74 times 10 to the 14 hertz. And then when you calculate the speed, this speed should be approximately 1.97 times 10 to the 8 meters per second. So remember, that the speed of light in vacuum is 3.0 times 10 to the 8 meters per second. But when you go from vacuum to another medium, there is a decrease in the speed of light. So the speed of light went from this 3.0 times 10 to the 8 meters per second to this 1.97 times 10 to the 8 meters per second. So there is a significant reduction, of the speed of light in the arm siren. Yes, it's this one. So they say in this exercise, a ray of light is incident on the surface of a block of pure ice at an angle of 40 degrees with the normal. Part of the light is reflected and part of the light is refracted. Find the angle between the reflected and refracted light. So let's try to sketch, what this problem is. So we have here, the surface. We have the surface. Well, we have air. These are my medians. The median one is here. The second median is just ice. Is ice. I will represent here the normal to the boundary between the two surfaces. And then we have an incident ray. We have an incident ray here. And then we have one reflected ray. And we have one refracted ray. This one will be the refracted ray. So what they want to recalculate this angle. That is the angle between the reflected and refracted ray. I will call this angle alpha. Now, what we know? We know that the incident angle is 40 degrees. So if the incident angle is 40 degrees, then now we know that the reflected angle of reflection, is also 40 degrees. Because the incident angle and the reflected angle, or the angle of reflection, is the same. So if the angle between the normal line and the boundaries between the two surfaces is 90 degrees, and the angle between the reflected ray and the normal is 40 degrees, then the angle between the reflected ray and the boundary of the two surfaces will be 50 degrees. Because 40 plus 50 is the 90 degree, that we have between the normal and the boundaries of the two surfaces. Now, what else I need to calculate? Well, I need to calculate, of course, then the angle of refraction. So I need to calculate this angle, theta sub 2. Because if I can find the angle theta sub 2, I will also be able to calculate the angle between the refracted rate and the boundaries between the two surfaces, and the boundary between the two surfaces. So I want to calculate zeta sub 2. So we say that n1, the sine of zeta sub 1, is equals to n2 sine of zeta sub 2. Now, we solve for zeta sub 2, and we know that zeta sub 2 is the sine inverse of n1 sine of zeta sub 1 over n sub 2. Now, we know that the index of refraction for the eyes would be 1.309. We know the index of refraction for the air is 1.00029. And we know the angle zeta sub 1, that's 40 degrees, because it's the incident angle. So we are ready to find zeta sub 2. So we are ready to find zeta sub 2, the angle of refraction. There is sine inverse of then 1.00023 sine of 40 degrees divided by 1.309. And when we calculate zeta sub 2, zeta sub 2 will be 29.4 degrees. So now we know that this angle is 29.4 degrees. The angle, zeta sub 2, that is the angle between the normal and the refracted rate, is 29.4. Now, since the angle between the normal and the boundaries between the two surfaces is 90 degrees, then if I find the angle between the refracted rate and the boundaries between the two surfaces, I will say that this angle will be 90 degrees minus 29.4 degrees. 90 degrees minus 29.4 degrees will be 60.6 degrees. So now I am ready to find the angle alpha between the reflected rate and the refracted rate, because it's the 50 degree, that is the angle between reflected rate and the boundaries of the two surfaces, plus 60.6 degrees, that is the angle between the refracted rate and the boundaries between the two surfaces, and this will be 110.6 degrees. So I found that this angle is 110.6. 110.6. Any questions so far? I have another exercise here that I would like to solve. Which is similar to one exercise that we did previously. Right? So we're going to be finding wavelengths and frequencies. So look at my next exercise. My next exercise says that the light emitted by helium neon laser has a wavelength of 632.8 nanometers in air. As the light travels from air into zircon, find its speed, its wavelength, and the frequency. All these speed, frequency of the helium neon laser, all these speed, wavelength, and frequency must be when it is in the circle, it's in the segment. So, what are we doing? We will be again, one more time, representing the boundaries between the two mediums. So we have air here, we have the circle here, and then now I have the boundaries between the two surfaces. Okay? And I have then my incident ray, and then I have my refracted rate. So we know that the index of refraction of the air is 1.000293, and in this case we can find the index of refraction of the circum in a table, and this index of refraction is 1.923. Now, what they ask you in the first case, they are asking about, what is the speed? What is the speed of the ray in circum? So to calculate the speed, I can use the relation that exists between the speed of light in vacuum with the speed of light in a medium different in vacuum. So I know that the index of refraction, so in this case, the index of refraction n sub 2, the index of refraction of the circle, would be equals to the speed of light in vacuum, which is c. Remember that c is the speed of light in vacuum is 3.0 times 10 to the 8 meters per second divided by the speed of the light in the medium, that in this case is the circle. So if I want to find the speed of light in this medium, I will say that V sub 2 will be equals to the speed of light in vacuum divided by the index of refraction n sub 2. So V sub 2 will be the speed of light in vacuum is 3.00 times 10 to the 8 meters per second divided by the index of refraction that I found. The circum is 1.923. And then we get the speed of light in circum is 1.56 times 10 to the 8 meters per second. So this is now the value of the speed of light in the circle. The next thing we need to do is to find the wavelength. And in the previous exercise, I just showed you, and also in the lecture, the relation that exists between the wavelength and the index of refractions for the two mediums. So we know that lambda 2, so wavelength in the medium 2, divided by the wavelength in medium 1 will be equals to the index of refraction in the medium 1 divided by the index of refraction of the medium 2. Of course, we can rewrite this equation like wavelength in medium 1 times index of refraction of the medium 1 is equals to wavelength of the medium 2 times the index of refraction of the medium 2. I want to find the wavelength. The wavelength where? In the circle, which is lambda sub 2. So we solve for lambda sub 2. And lambda sub 2 would be lambda sub 1 times n1 divided by m sub 2. So lambda sub 2 would be divided by m sub 2. So lambda sub 2 would be the wavelength in air, which is 632.8 nanometers times the index of refraction of the air, which is 1.000293, all divided by the index of refraction where in the circle, which is 1.923. So we're calculating lambda sub 2. So the wavelength of this LED neon laser light would be 329.2 nanometers. So this one is going to be the wavelength of the light that in air have a wavelength of 632.8 nanometers. But now in the new medium, there is circle. We have one more case. We have to calculate the frequencies. Well, to calculate the frequency, I know that the frequency is not going to change. So the frequency of the light when it's propagating through the air, and the frequency of the light when it's propagating through the circle is going to be the same. The frequency is not going to change. But I know enough information to calculate the frequency because I know the speed of light in the circle, and I also know the wavelength of the light in the circle. So if I know for the calculations in part C that the speed of the light in the median is equal to the wavelength of the light in that median times the frequency. If now I want to find the frequency, I will say that the frequency is equal to the speed of the light in that median divided by the wavelength in that median. So if I want to find the frequency, I will say that the speed of the light in circle, which is 1.56 times 10 to the 8 meters per second, divided by now the wavelength in that same circle, there is 329 times 10, 329.2 nanometers. But I will convert the nanometers into meters. So remember that 1 nanometer is the same that 1 times 10 to the negative 9 meters. So basically, you have to multiply by 10 to the negative 9 the wavelength in nanometers. So we say that this is 329.2 times 10 to the negative 9 meters. And we're going to get a value of frequency that would be in hertz or 1/seconds. And when you calculate that frequency would be 4.74 times 10 to the 14 hertz. Times 10 to the 14 hertz. And here we have now the frequency of the light in this circle. So we found the speed of the light in the new medium, the wavelength in the new medium, and the frequency in the new medium. let's try to solve. Let's try to solve the next exercise. This next exercise, is very interesting because we have two mirrors that are parallel, and those mirrors are at a distance of 1 meter. And you want to find how many times will the incident beam that is given, how many times it will be reflected by each of the parallel mirrors. So how many reflections are going to occur here? So basically, what they say is you have those mirrors, and then you have this incident ray, and then this incident ray makes an angle of 5 degrees, with the mirrors. So that means that there will be one reflection like this here. There will be later another reflection like this. There will be later another reflection like this. There will be later another reflection like this. Another reflection on like that. So basically what we want to do is to count how many reflections we're going to have in the left mirror and how many reflections will we have in the right mirror. This is what we want to basically find out. So we will have to use some of our knowledge of trigonometry in this case. So I will now make a sketch of the two mirrors. There's only a small part of the two mirrors. So here I have the left mirror. Okay. It continues, so I am now trying to represent the whole mirror. There's only a section of it. And I also have the right mirror here. And again, I'm trying to represent just only a section of it, right? And then we know that the distance between them is 1 meter. And then we know that there will be an incident ray. And this incident ray makes an angle of 5 degrees. Let me just use another tool. Sorry. Let me see if I can just use the straight line tool. So you have this line here, what is the incident ray? And I have again the line here that is when it's reflected. Okay, so this is the incident. And this is when the reflection occurs. Now, what I know that the angle is the angle of reflection is 5 degrees. So if I do a normal here, I will have that this angle is 5 degrees. And this angle is 5 degrees as well. Okay, So if I want, I can calculate, you know, and let me just do something to make it easier to understand, the triangle that I will get. So let me make a straight line in another color here. So this angle between this straight line and the incident rate is 5 degrees. We know that. This one is 5 degrees also. And then I will call y the distance between the base of the mirrors and the first point of incidence of the incident rate. The first point of incidence of the incident rate. We'll call this y. So if I know this angle is 5 degrees, I can find y because I know this side that is 1 millimeter distance between the mirrors. I basically have a triangle. I have the distance between the mirrors that is 1 meter. I have the angle, right? That is 5 degrees, so I can calculate y. That is the distance between the bottom of the mirror and the first point of incidence of this angle. So I will say that the tangent of 5 degrees will be opposite side over adjacent side. So it will be y over 1.0 meter. So you can say that 1.0 meter tangent of 5 degrees is equal to y. So y will be 0.09 meters. 0.09 meters. Now, if we extend this angle, this rate, then this distance here is 2y. This one is 2y. So I can calculate 2y, and 2y will be 2 times 0.09 meters. So 2y will be 0.18 meters. 2y will be 0.18 meters. 0.18 meters. Now, the height of the mirrors, is 1 meter. Is 1 meter. How many reflections we will have in the right mirror? Number of reflections on the right mirror. The number of reflections in the right mirror will be the height of the right mirror divided by 2y. Because the first reflection occurs here at 2y from the bottom of the mirror. So the number of reflections will be the quotient between the total height of the mirror and 2y. Now, what we know, the total height of the mirror is 1 meter, and 2y is 0.18 meters. So you would have in the right mirror, when you do this quotient for this operation, you get 5.55 P5 which is going to be really, because you cannot have 0.55 for reflection, so you will have really 5 reflections in the right mirror. So you have to round down, right? Because that 6 reflection is not gonna really hit the mirror. So there is not going to be a 6 reflection because there is no mirror to have the 6 reflection. Now, what happened with the left mirror? The number of reflections in the left mirror is going to be a little bit different because the first reflection here is going to occur, above this value of y. So you choose strat to count the number of reflections here. Y from 1 meter, y, there is this distance, y from the length of the mirror, from the height of the mirror, that is 1 meter. And then like that, divided by 2y, you can find because the next reflection will occur at 2y from that first, and the next will occur at 2y. So later, divided by 2y, that value, you will find the number of reflections in the left mirror. Of course, you have to remember that you had 1/3 reflection here, and you have to add to the number you will calculate. So you will say that the number of reflections in the left mirror will be the height of left mirror minus y over 2y plus 1. So that means that this will be 1.00 meters minus 0.09 meters divided by 0.18 meters plus 1. That is going to give you 6.06, which is going to be 6 reflections. This plus 1 is due to this initial first reflection that we had, to the incident rate. So how many reflections we have in the right mirror? We have 5 reflections. How many reflections we have in the left mirror? We have 6 reflections. We have 6 reflections. If you wanna just analyze this, you can think in something like this. Let's say I have my left mirror, and in my left mirror, the first reflection occurs at y units from the bottom of the mirror. The second reflection is y plus 2y, so it's at 3y from the bottom of the mirror. The next reflection is going to occur at 5y from the bottom of the mirror. The next will occur at 7y from the bottom of the mirror. The next at 9y from the bottom of the mirror. And the next at 11y from the bottom of the mirror. So if we multiply, 0.09 times 11 that would be 0.99 meters, which is less than the 1 meter of the mirror. So yes, there is enough space to have 6 reflections here. We have enough space to have here the 6 reflections. Because 6 reflections takes 0.99 meters. Now, when you go over the right mirror, you know that your first reflection is going to occur at 2y from the bottom of the right mirror. At 2y, look at this point. This is where the first reflection on the right mirror occurred, and this is 2y from the bottom of the right mirror. So this one is occurring at 2y, and then we have 5 reflections in the right mirror. So we have then, 4y. We have another one at 6y. We have another one at 8y. And we have one more at 10y. When you multiply 10, in this case, go to 0.9, we have that 10 times 0.09 will be 0.9 meters. 0.9 meters. Right? So we have, in this case, 0.9 meters. So 10y is 0.9 meters, which is less than the 1.00 meters. So what we have basically enough space just to have the 5 reflections. To have the 5 reflections on this side. This right side of the mirror. Okay. So this is just a solution of this problem. It's a very interesting problem because it makes us use some tools that we know from trigonometry, right? So use tools of three, and I really find it, interesting because also we are using, what we know about the angular reflection. So that relation that exists between the incident angle and the angular reflection,